Merry Christmas! Hallelujah, very good. Okay, so 5-3 continued. We talked a little bit about the first derivative test. We did talk about the first derivative test, didn't we? Did I do an example of that? Do you want me to do an example of that? I think maybe I should. Okay. So here's an example of using the first derivative test. Use the first derivative test. Well, the first derivative test was on chapter 2, and then we took the second derivative. No, I'm just. Oh, I already told that joke. I don't remember which class it is. Okay. The first derivative test. Use the first derivative test to find the local, in this example I think is in your book, local and absolute extrema. That means that
defines absolute without endpoints.
if it doesn't have any endpoints, then you can't find them. Okay, so in this case, there you can't really find. Oh yeah, you can, because if you know it's decreasing on a certain interval forever, then you could figure it out. So if this is your function, okay, and I'm just going to go through and tell you that the derivative of this comes out to be, I don't want to go through everything because I'm in a rush, comes out to be e to the x times x squared plus 2x minus 3. If you took the derivative of the first times the second plus the first times it, because this is product rule. And then what they do here is to find out where you can have extrema, you have to see where the derivative is either undefined or is 0. So in this case, you can factor this part, and it comes out to be x minus 1 times x plus 3, which means that my derivative is 0 when x equals 1 or x equals negative 3, right? Okay, and just believe me that that's a derivative. You could do it, I'm sure. So then what you want to do is kind of make one of these little sign tables, okay? And put numbers on here. So negative 3 you want to put like over here, and then you want to put like 1 over here, and then you want to see what the derivative is doing to the left and the right of those points, okay? And so to the left of negative 3, what's always going to be true about this factor of this factor derivative? It's always positive, because no matter what number I plug in there, it's always going to be positive. And so this is always positive, so you just really have to look at this. So if I plug in a number to the left, like negative 4, okay, and then I'm going to get negative 5 times negative 1, which, well, what's a negative times a negative? Positive. So over here, I have a positive. So this means that the derivative is positive, which means my function is increasing, okay? Increasing, so f of x is increasing. Yes? No? Maybe? Did I do that right? I think I did that right. And then if I plug in a number between negative 3 and 1, what's an easy number to pick between negative 3 and 1? 0, right? So if I take 0, negative 1 times 3 gives me negative 1. So that means that my derivative, so this is f prime over here. F prime of x, or g prime of x. I guess this should say g prime of x too. And I guess this should have been g of x in the very beginning. Okay? So that's negative, so that means that my derivative is decreasing. And over here, if I plug in a number to the right of 1, like 2, I get out a positive, which my function is increasing. My function is increasing, my derivative is positive. Okay? So if the derivative changes from positive to negative, what do I have at that point? I have a relative or local maximum. Okay? And if my derivative changes from negative to positive, what do I have? Hello. Relative minimum. Okay? Now, this part of it, as x gets very, very, very large, this thing would also get very large. So if I think about the, if I think about the graph over here, okay, this graph is, on this end, it's going to kind of go like this up forever, okay? And so it's going to a minimum, right, it's going down, and right here you have a relative minimum, which means it must go up here, okay? And then you have a relative maximum, and then it comes down, this way, okay? And this number, if I do plug in 1, what do I get out if I plug in 1? You guys know? What do I get out if I plug in 1? 1 minus 3 is negative 2. And if I plug in 1 in here, I get times e to the 1 times e. So that's a negative number, right? It's a negative number? You understand that? Okay. Now over here, as I go down this way, if I take the limit as x goes to negative infinity, that's a negative infinity. That's a really bad infinity. Okay. Negative infinity. The limit as x goes to negative infinity, this number will still never be negative, right? It'll always be positive. And this number is a positive big number, right? And this number kind of goes to 0. So the biggest this function is ever, or the smallest this function is ever going to get over here, it has an asymptote at 0. And so what that tells you, I kind of drew this, if this point, right, is at 1 comma negative 2e, right? That's what that point is right there. And it never goes below 0. What else could you tell me about this point besides being a relative minimum? If it never goes, absolute. It's an absolute, because this, as I go to the left, it never goes lower than 0, you see? And so this is actually an absolute minimum. That's kind of weird, and I had a look, and they said, oh, in the book, look at it at the left, what's happening to the left and the right. This one, it just goes up forever. But on this one, it approaches an asymptote. So this is a relative minimum. Absolute.
How did you know it had an asymptote?
How do I know it has an asymptote? Because if I take the way you find asymptotes is the limit as x goes to infinity and negative infinity. Okay? So if I plug in infinity, very big horizontal asymptote, because this I could write as x squared minus 3 over, if I plug in a negative number, right? Say I plug in a very big negative number, right? Like 1 million or something in here, right?
Negative 1?
No, it's just, oh yeah, negative 1 million. It's still going to be negative 1 million squared. Over here, if I plug in a negative big number, it's like e to the 1 million down here. Yes?
Yeah.
Right? So raising something to the millionth power is a lot bigger than a million squared, right? And so this down here is going to way outweigh this. And so
What is it? How can you divide it?
because something to a negative power e to the negative 1 million, right, is the same as, yeah. So that's kind of a tricky analytical thing. Okay? Okay. So now we're going to learn about concavity. You ready to learn about concavity? So I have to tell you something funny, but I can't be recording it. So did you guys? We're recording again. So now we're going to talk about concavity. Concavity and inflection points, really, because concavity goes along with inflection points. So if a curve goes like this, that's called concave up, right? Concave up. And if a curve looks like this, that's called concave down. So basically, if it holds water, and curves, they change their concavity as you go along. So if it's concave up, it holds water. If it's concave down, so happens that if a function is, so say this is, I should just look at my notes. Okay, so say you have a function like that, kind of looks like this. Okay, at this point, this particular function changes from being concave up to concave down. All right, and that point has a name, and that point is called an inflection point. Okay, an inflection point is a point where concavity, the definition of an inflection point, concavity changes sign, and there is a tangent line. Okay, so the function has to be continuous, and it has to have a derivative at that point, right? Otherwise, you couldn't have a tangent line. So you can't. So for something that looks kind of like this, like if you have an asymptote here, and it's concave up here, and then it's concave down here, you can't really say that this point in the middle is an inflection point because it has to have a tangent line.
What if it goes to like infinity?
If it goes to infinity, that's okay, because you can have it like here. If this were straight up and down, you can't have a vertical tangent line, okay? But you couldn't have it doing something like this, and then doing something like, I don't know, like this, straight, and then kind of curving, because it wouldn't have a derivative there if the slope changes abruptly, or if you have an asymptote, or if you have a hole in the graph. Okay, so some tests to tell if it's concave up or concave down. It's also where the derivative is increasing or decreasing. Okay. Which means that the second derivative is positive or negative. Okay, so again, what I just said, what did he just say? Okay, if f prime of x is increasing, in other words, f double prime of x is positive, okay, then concave up. Okay? And then vice versa, if f prime of x is decreasing, meaning f double prime of x is negative, then concave down. Okay, so for example, and in order to test for concavity, you need to have a twice differentiable function. You know what they're talking about? Twice differentiable function. It means you can take the derivative twice. So for like y equals 3x, a straight line, you take the derivative once, you get 3, and then you can take the derivative again and get 0, but you can't really, that doesn't tell you anything about the concavity because it's 0, right? So, but if you have like an x squared function, right, say we have test for concavity, I'm going to make up my own interesting problem. For f of x equals negative 3x squared plus 7x. Okay? So if I want to do that, what's f prime of x? What's f prime of x? Come on, you can do it. Negative 6x plus 7. What's f double prime of x? Okay. And, oh, that's a bad example. That's equal to, oh, that's true. No, it's not a bad example. Negative 6. So what can you tell me about this particular function? It's always concave down, right? And so, which agrees with what shape that is. What shape is this? It's an upside down parabola, right? And so it's always concave down. I'm not sure where that upside down parabola is, but it's always concave down. Uh-huh. Yeah? No?
Is that it?
Is that it?
Also,
What?
the only time it would change concavity is if it has a variable in the double prime function. Is that what you're saying?
Ah, very good. The only time it would change concavity is if it has a variable in f double prime. Yeah, yeah. Good. Yeah, and that's what they mean by, that's not what they mean by twice differentiable, but like a 3 times differential. That's a good point. So then we have more complicated functions like find where y equals 3 plus sine of x changes concavity, or find the concavity. Okay, how would I describe it? How would I write that?
Find the point of inflection.
I think describe
Describe the
the concavity of y equals 3 plus sine x on, they'll give you an interval, 0 to 2 pi. Okay? So the first thing I have to do is find y prime. What's y prime? Easier. This is a case where y prime is easier than y, right? What's y prime? Cosine x. And what's y double prime? Negative sine of x. Okay? And so you guys probably are pretty good at this. So we're just looking at the interval to 0 to 2 pi. What does negative sine of x look like? Y equals negative sine of x. Yeah, it starts down and it does one cycle in 2 pi radians, right? Okay? So this graph describes the concavity of this function, which is 3 plus sine of x, which is a sine function that starts up here. Whoops. Yeah. Goes down and goes back up. So according to this, right, concavity is negative. Does it appear that from here to here, so this is f prime, f double prime of x, right? And this is f of x, if this were f of x, okay? Does that make sense? See how the f double prime is negative? It's concave down, yes? Okay? Here, f double prime is positive, it's concave up. And this point right here is called a, this is called a point of inflection, right there. And the point of inflection is where it changes concavity from concave up, or concave down to concave up, or concave down up to
So how do you
concave.
write the answer to that?
How do you write the answer to that? You would say something like increasing, you would write something like concave up on 0 to pi, right? And then you would just say concave down on pi to 2 pi. That's all if they ask you to describe. And there's a pi right there.
Wait, why would you graph the f double prime?
Why would I graph the f double prime? I guess you wouldn't have to, but I think it's easier to see where the function is negative. You could say where is the graph of y equals negative sine x negative, right? Where is it less than 0 between 0 and 2 pi, and it's less than where is it negative sine x less than 0? That's like saying where is sine of x? Where is sine of x? Is that the same as saying where is sine of x greater than 0? Yeah. Where is sine of x? Right? If I multiply through by a negative, the sign flips. Okay? So I could say where is sine of x bigger than 0? Okay? And so sine of x is positive from 0 to pi. And sine of x is negative. So you could do it that way too. Yes.
Does it matter if you have like square brackets or curved brackets when you're doing concave?
Yeah, and this, you want to have curved brackets because there's not really any, since this is going to be a point of inflection every time, you don't really have a, it's not concave up or concave down. What?
Even at like the endpoints, like at 2 pi and 0.
Yeah, because right here, it's continuous, right? So right here, it's going to change concavity, right? So right at that point, it's neither concave up nor concave down. Hey, for someone who's very untrained to do this problem anyway, so it'd be a good place to look at it. I think I'm recording now, right? So Austin asked, why would we ever want to know about concavity or anything like that? And this is a page. This is a page from your book. Let's see, can I move this over a little bit? There. That's better. And then I could grab this and move it over and show it to you. Okay? And so for a population growth model, like over here, okay? Find the logistics. So here's a whole bunch of data, population in Alaska, okay? Use the regression equation to predict Alaska population in 2020. Find the inflection point of the regression equation. What significance does the inflection point have in terms of the population growth of Alaska, okay? And what does the regression equation indicate about the population of Alaska in the long run, okay? So if this is the, this is a graph of the second derivative, okay, of this logistic growth function. You know what a logistic growth function looks like? Kind of goes up like this and then it kind of levels off, right? So where the second derivative is 0, which means it's changing from positive to negative, that's the point at which the population growth, it's still increasing, but it's starting to go up slower. You know what I mean? And a lot of time, like in stock markets, you know, like if you're looking at a stock, you know, it's going up really fast, and then it'll, at that point of inflection, it's still going up, but it's not going up as fast. That might be the time, it's getting saturated or whatever. Too much of this is getting bought. Maybe I better sell before it starts plunging off the cliff, you know?
In college, they had a class called business calculus.
Yeah, and call it in business hunting. You know, you kill too many rabbits, and then the population, you know, maybe the population of rabbits or pheasants or whatever, you know, but population growth with animals, they use those kind of logistic growth models all the time. So, yes, sir.
So do we set the second derivative equal to 0, and that's how we find it?
But you have to make sure the second derivative is defined at that point, or not defined, but that it has a
differential.
Yeah, it has a tangent line at that point. So it can't have a vertical tangent.
At least it could.
So then we just set it equal to 0 and then solve for it to find the x, and then plug the x back into the original equation to find like where the point of inflection is.
Yeah, how would you do it?
We'll talk more in a second, okay? So points of inflection. So we're gonna find a point of inflection. Didn't we just do that? Did we find the concavity? Let's do a complicated one, okay? So going back, we're gonna find the point of inflection. Find the PIs. Hey, pay attention there, Tanner. Find the PIs for y equals e to the negative x squared. I haven't talked about the second derivative test yet. Okay? Y prime is, I'm just going to tell you and simplify. I think you could come up with this. It's negative 2x e to the x. Is that what it is? Negative 2x e to the negative x squared. Would you agree with me there?
Yes.
Okay. Y double prime, in the interest of time, I'm going to simplify it down for you. Okay. It comes out to be this. Y double, you have to use a product rule and all that, but if you squish it down and you factor out e to the negative x squared from both parts, you end up with e to the negative squared times 4x squared minus 2. Okay? And to search for points of inflection, you don't just find out where the, you can't just find out where the x is equal to 0, because you could have a point, you could have a second derivative where it's equal to 0 and still not have a point of inflection there. So you have to check to the left and the right and make sure that the graph is changing, or the second derivative is changing from positive to negative. Does that answer your question, whoever asked that question? Okay, so you want to set this equal to 0, but that doesn't tell you this for sure is a point of inflection. And so when is e to the negative x squared equal to 0?
Never.
Never. Very good. Never equals 0. And then to find out where this thing is equal to 0, I just do a little math here. I get 4x squared equals 2. I get x squared. X squared is equal to 1/2. So x is equal to plus or minus, when I simplify this, root of 2 over 2. Root of 2 over 2. Sorry, not the whole thing in brackets like that. It's root of 2 over 2. So why is it root of 2 over 2? Because it's a square root of 1 over the square root of 2, and then if I rationalize it, it comes out to. Okay? So then what you do is you draw your number line thingy. Okay, let's put arrows on the end because it goes on. Okay? And so this thing you don't ever have to worry about because it's always positive. You guys understand why that's always positive? Even if I raise it to a negative power, it's still going to be a positive number, small positive number. But so on this graph, for what you do is you put f double prime of x, okay, and then you put x down here, and well wherever, and either or vice versa, okay, and then you put these 2 points on here. One is root of 2 over 2, and one, negative root of 2 over 2, and one is positive root of 2 over 2. And then you plug in some values. So I have to know that negative root of 2 over 2 is about negative 0.7 or something like that. So I'm going to plug in a point to the left of that, like negative 1. This one, it doesn't matter because this is always going to be positive, right? So if I plug negative 1 in here, that gives me a positive number. 4 minus 2 is what kind of number? Positive. What's a nice number in whoops. Uh-oh. Positive, don't do that. Okay, so positive. I don't know how to fix it. So this is positive. In between negative root of 2 over 2 and root of 2 over 2, what do I have? 0. So what's 0 minus 2? Negative. And what's over here? Positive. If I plug in a number bigger than 0.7, like 1, I get 4 minus 2, which is 2. So I get out that this is positive. So what this means is here, the concavity is up, right? Then the concavity is down all through here, and then the concavity is up through there. And here, what do I have? I have PIs, okay? PI, because the concavity is changing from negative to positive. Okay? Yes? And if you actually graph this function, it actually looks like something. I think it looks like a bell curve. Does it? Yeah. If you graph it, it actually looks kind of like this, and then like this, kind of like, you know, the bell curve. And here's your points of inflection at positive root of 2 and negative.
Like the two things don't end up going like up at all.
It doesn't go up. No, it's just.
Yeah.
But yeah, and it doesn't really matter because it's always concave up. That if it did, it did. But I'm not sure that it doesn't look like this. But then I graphed it and I found out that it does.
So it wouldn't really hold water.
What?
That wouldn't really hold water.
It wouldn't hold water, but it's still considered being concave up because it's the derivative is increasing. Yes.
So the positive, negative, positive thing, is that for the double or the second derivative?
That's for the second derivative, but when you graph other stuff, then you look for both of. So when you try to graph, there's some in your homework, you're going to try to graph functions from the first and the second derivative. So you look at what the first derivative is doing, you look at what the second derivative is doing, and then you test for.
So like that line you drew on the bottom, that's.
I was just trying to show you the
just
concavity.
F of X?
What?
It's like, and that's just f of x. Not
Yeah, that would
f
just
of
be
x.
f of. It's not really f of x, but it's showing you that that f of x is up, f of x is down, f of x is up again. But what f of x really looks like is more like this. Okay? I think I'm just going to have time to teach you the second derivative test. Okay? You ready for the second derivative test?
Sure.
And that's kind of a good one too.
How will we know when the first derivative test and the second?
It'll tell you. Okay? And the second derivative test doesn't always. The second derivative test doesn't always work. Okay? So
That's not disheartening at all.
yeah. So the second derivative test, and I'm not going to get to the curve sketching thing, which is the stuff that I was hoping to get to, but try to do it. Okay. Second derivative test. If f prime of c equals 0 and f double prime of c is less than 0, then, so this is second derivative test for relative extrema. That's what you're checking for when you're using the second derivative test. So that if it works, the second derivative test is a really quick way to check if you have maximums or minimums at those points. Okay? And if f double prime is negative, so what this is, if f prime of c is 0, so if the derivative is 0 and it's concave down, what do you think has to be true? What are you at?
The second derivative is negative.
If the second derivative is negative, sorry, what does that mean about the function at that point? The slope is 0, but it's concave down, so what type of point do I have to be at? At a relative maximum, okay? Relative maximum. And the second part of the second derivative test says if f prime of c is equal to 0, so it's a place where the slope of the curve is equal to 0, and the second derivative is bigger than 0, that means it's concave up and the slope is 0, so what do I have there? It's, what do you call that? A relative minimum. Relative min. We'll do an example in a second. Okay? And test fails. Test fails if f double prime of c equals 0 or d and e, or it's undefined at that point. So if you get a second derivative of 0, like if you did tried to do this with, well, we'll do one in a minute. So find the local, so the easiest things to use second derivative tests are, sorry, I went too fast. I'll post these. You want to look in. Use the second deriv test to find relative extrema of y equals x cubed minus 12x minus 5. Okay? So I stole this example, I think. So y prime is 3x squared minus 12. And so you set this equal to 0 to find out where the first derivative is equal to 0. So I can do that, and I could factor out a 3, can I? X squared minus 4, whoops, x to the x, no. X squared minus 4 equals 0. So x equals plus or minus 4, right? 2. I knew that. Come on, I was doing so well. Then you want to do y double prime. What's y double prime? Hello? 6x. Right? So then what you want to do is take these two values and plug them in. So y double prime of positive 2 is what? 12. And y double prime of negative 2 is negative 12. So at 2 comma something, I have a what? Since it's the derivative is 0 and the second derivative is positive, what do I have? Relative minimum. Relative minimum. And then at negative 2, what do I have? A relative maximum. Okay? And so kind of if you graph this, this is a cubic function, right? And so what I know is with this cubic function, at negative 2, and I know because it's a cubic function with a leading positive coefficient, it goes from down to up. So I have to know that at negative 2, I have a relative maximum, and then at positive 2, I have a relative minimum, right? Like that. Isn't that cool? How about that? Okay? And then I want to do one more where you have an undefined thingy.
Did you just plug your negatives back into the function?
Yeah, then you could plug 2 back into the function and find the actual y values that goes. Yeah. Okay. And lastly, I just want to show you with y equals x to the 1/3 power, and I say find the rel extrema with second derivative test. Watch. If I do this, y prime is equal to 1/3 1/3 x to the 2/3. Would you agree with me there?
Yes.
It is, okay? But what's true about this? I'll tell you what's true about it. It's undefined at x equals 0, okay? So if the first derivative is undefined, what's true about the second derivative? It's undefined as well. So the test fails, but because this, if you were to graph it, it has a vertical tangent there, and so and there's no max or min at that point anyway, okay? And this one doesn't have a relative maximums or minimum. Okay?
So if we get one like that, can we just say test fails?
Test fails, yeah. Okay? What?